Tim Vanderhoek. I'm the engineering manager responsible for the FPGA AI suite. I've actually spent my entire career working with FPGAs and with Altera. The funny thing is that about 20 years ago, I was choosing between an internship at Altera and one at a company doing embedded design. And I was told by my mentors that embedded design is crazy hard, don't go there. And so I went to Altera. And now here I am, 20 years later, managing a team where one of our main responsibilities is to develop example designs for the AI suite in the embedded space that are explicitly easy to use and not crazy hard. It's funny how the universe sometimes puts you in the same place regardless of what decisions you make. In this section, I'm going to show a typical interaction that an FPGA engineer might have with the AI suite when they decide to optimize the IP configuration to achieve a specific performance and area target. We're going to start with a YOLO V8 graph and target Agilex 5, and then we'll progressively optimize the IP configuration until we achieve approximately a 3x increase in performance while targeting a specific area budget. This is a reminder of the flow that Audrey showed earlier. I'm going to be addressing specifically the transition section number 2, where we take the model that was created by the data science team, and then we optimize that IP configuration, specifically targeting that model for a specific performance and/or area budget that we have or we need to achieve in order to make our product. I will show how this flow allows you to quickly see the full performance and area estimates without ever running Quartus. And this will enable easier and faster design closure. Typically, a data science expert or a team of experts will select a machine learning model that is appropriate for the problem. YOLO V8 is a reasonably modern and well-known image network that can be used for classification, object detection, semantic segmentation, and even pose analysis. It's considered to be an open source network. It comes in 5 size variants: nano, small, medium, large, and extra large. For our problem today, I'm going to assume that we need the YOLO V8 Nano classification model. This is a classification model, which means that it looks at an image and it says dog or cat. Agilex 5 is our newest FPGA family, and it includes tensor DSPs that enable high-performance machine learning while consuming a relatively small number of the DSP resources on the FPGA. I've chosen the Agilex 5 family today because of its tensor DSP, but our AI suite supports machine learning on families ranging from ARIA 10 through to Agilex 7. Furthermore, within each family, such as Agilex 5, all of our FPGA devices in that family support AI using the FPGA AI suite, allowing you to choose the device that is best for your overall system specifications. For the IP optimization process, as mentioned, I'm going to iterate through several different architectures here, all without using Quartus. The command shown on this slide calls the DLA compiler. In this example, the data science team has already created the intermediate graph data by running the OpenVINO Model Optimizer tool. The compiler will accept this intermediate representation as one of its inputs. And then it's going to create an instruction stream which includes all of the graph weights. This instruction stream is used to control the IP that's on the FPGA, and it will enable that IP to execute inference operations on the FPGA. If you are ready to use the instruction stream, then it can be dumped to a file and will be sent to the FPGA, which has the IP on it already. In the case shown here, however, we are asking the compiler to use the instruction stream to perform a performance analysis. This will cause the compiler to run the performance estimator tool that will go through the entire FPGA instruction stream, and for each instruction, it will estimate the associated latency. Based on this, it will come up with an overall performance or latency estimate for the graph. Now, obviously, there are some buried assumptions in here, such as the Fmax of the IP, and such as the bandwidth to external memory, if you are using external memory. These options, such as the Fmax assumption, can be changed by various command line options to the compiler, which I have not shown here. This option simply tells the compiler where the data from OpenVINO has been stored. This tracks all of the model weights and all of the layers. As Audrey explained earlier, the FPGA AI Suite IP is built as a configurable overlay. This means that it can dynamically switch between different machine learning graphs, as Audrey explained, but it also means that we can customize the IP to create either larger or smaller instances on the FPGA, depending on our system needs. The Arch file shown on this slide is one of the inputs to the DLA compiler, and it specifies that IP configuration. The AI Suite includes with it a number of example Arch configurations. And in this case, I have chosen one of the example Arch configurations named AGX5 small softmax. When we run the compiler, it prints about a screenful worth of output, including the performance analysis that we asked the compiler to perform. I've drawn a box around the performance estimate, which is 277 frames per second. Further up the input stream, we can see a warning that I've marked in red text, which says the input graph has been split into many subgraphs. Now, the AI Suite has the ability to split a graph into multiple subgraphs so that layers which are not presently supported by the IP can be executed on an optionally attached host. The example runtime that is included with the AI Suite example designs will seamlessly stitch between the FPGA and a PCIe attached host, or between the FPGA fabric and an SoC attached host in order to execute inference for this graph. So even though we see this warning, which I've marked in red text, this graph is perfectly functional with 53 subgraphs, 26 of which will execute on an attached CPU. Let's take a look at the model analyzer report file, which is created whenever we run the compiler with a model. This file contains layer by layer information to help us understand the messages from the compiler. At the top of the file, we see a list of layers that are unsupported by the FPGA, or rather by the IP on the FPGA. Looking farther down, we find the reasons for why those layers are unsupported. The key message is marked in red text and tells us that we need to enable the sigmoid activation in order to support the swish layers that are included in YOLO V8. Remember, earlier on we provided an Arch file to the DLA compiler? This Arch file told the compiler how we wanted to configure the IP on the FPGA. The compiler needs to know this configuration so that it can generate an appropriate instruction stream for the IP. When it's time to actually generate the IP and put it on the FPGA, we're going to use a tool called the IP generator, which is shown by that middle box, in order to create an instance of the IP, which can then be included in Platform Designer and compiled into an FPGA bit stream. Or it can be used outside Platform Designer if you prefer to use a pure RTL flow. It's useful to understand a bit about the IP that will go on the FPGA, even though today we're not going to compile that IP or use the IP generator. When we look at the diagram on the right, we can see that there is a convolution array, and the Arch file configures the size and the dimensions of this array, Those are the K vector and C vector parameters listed at the very top of that file on the left-hand side. Similarly, there is a filter cache over here that stores the graph weights. Buried inside the stream buffer, or the input feeder, we renamed it, is another cache that stores the feature data. Furthermore, the bus width connecting many of these modules is also configurable. Very importantly, at the bottom right-hand side is this section called the activation and pooling modules. The Arch file allows us to configurably either disable any one of those modules to save area, or we can enable it and include it in the IP. Let's modify the Arch file to include the sigmoid module. The text in green shows what we changed in order to enable this module. The AI suite includes a tool called the Architecture Optimizer that will automatically set many of the parameters in this Arch file for you so that you don't need to know them or understand them or even think about them. However, we made the design decision that the optimizer will only change parameters related to purely the performance of the graph. Changes that affect the performance of the IP. Changes that affect the functionality of the IP do need to be made explicitly by the user. Because we are enabling a sigmoid module, that changes the functionality of the IP because it changes the set of graphs that are supported on the IP. And as a result, we need to explicitly make that decision here in the Arch file rather than trying to use the tool to do it for us. Another important parameter that must be explicitly set is shown near the top of the Arch file. This is the Arch precision parameter. Increasing or decreasing the Arch precision of the convolution array changes the numerical accuracy of the inference. And as a result, the Arch optimizer will not change it automatically for you. We've set the default Arch precision in all of our example architecture files to use the DSP mode that is the most dense for machine learning. In the case of Agilex 5, this means that all of our example Arch files will map onto the tensor mode of the DSP. However, there are times where you may want to use a lower architecture precision. For example, if you are using externally attached memory, then you may want to reduce the bandwidth required to that memory. Reducing the Arch precision will reduce the bandwidth requirements. Alternately, you may want to reduce the number of M20K blocks required by the IP. Again, changing the Arch precision to a lower value will reduce the number of on-chip M20K blocks required. Conversely, of course, you might have some graph that is very sensitive to numerical accuracy. In that case, you might go all the way up to an Arch precision of block FP16. Now that we've updated the Arch file configuration, let's rerun the DLA compiler. We're going to use the exact same command as was shown previously, except this time I've specified the modified architecture file. The input graph is unchanged, but the instruction stream created by the compiler will be different due to the changes in the Arch file. As before, we've asked the compiler to do a performance analysis, and the new performance analysis will reflect the new instruction stream. Now that we've run the DLA compiler with the modified Arch file, let's take a look at the model analyzer report again. This time, we see a different message that says, all layers are supported. This is excellent. It tells us that for YOLO V8 with this particular head, the graph has been entirely mapped onto the FPGA and does not use the attached host at all. Now, for some variants of YOLO V8, such as pose analysis, we would have had to keep some post-processing layers on the attached CPU. But in this case, everything was mapped to the FPGA. The example runtime will still operate with a host, but for this graph and this configuration, it would be easy to execute inference on the FPGA without using a host at all, the control could be as simple as a state machine. The Model Analyzer report also contains a section that lists unused or redundant activation modules. These are activations that are enabled in the Arch file, but which are not used by the graph that we compiled through the compiler. For example, the clamp module is listed as one of the enabled but unused modules. We may choose to leave the clamp module in the IP because perhaps we want to be able to execute some future graph that includes a clamp. However, if we know that we will not use that clamp module, or alternately, if we know that we are willing to use Quartus to recompile the IP when necessary, then we can simply disable the clamp module and we will reduce the amount of area required by the IP. Looking at the compiler, we see that the new performance estimate is 335 frames per second. This is obviously an improvement over the previous estimate of 277 frames per second, shown on the left-hand side. Actually, the performance improvement is even larger since the old estimate was based on the instruction stream for the FPGA, but did not look at the instruction stream for the CPU. Remember, the switch layers were executed on the CPU. So as a result, that old estimate was actually a little bit optimistic. That means our new estimate is not only faster, it's also a higher quality estimate since everything is on the FPGA. Since the graph inference executes entirely on the FPGA, it is interesting to look at the Fmax assumption. The default Fmax assumption for Agilex 5 is 350 megahertz. But the actual Fmax in Agilex 5 will vary significantly depending on whether the design targets an E-series device or a D-series device. As well, the speed grade of the FPGA will also have an effect on the Fmax. This default value of 350 megahertz is reasonable for the E-series devices. For the D-series devices, we're seeing Fmax values in excess of 600 megahertz. The performance of the IP will increase roughly in proportion to the Fmax. If you have attached external memory, or if you have an attached host, then either of those could create an additional bottleneck on the performance that might result in sublinear scaling. However, in the case where neither of those are used, neither external memory nor the host, then the performance of the IP will scale linearly with regards to the Fmax. The DLA compiler, based on the command line options we gave it, also performed an area estimate. This area estimate depends only on the configuration specified in the Arch file. It will not change regardless of which machine learning graph is given to the DLA compiler. In fact, if we had wanted, we could have asked the DLA compiler to perform an area estimate for us without even specifying an input graph. The key numbers in this area estimate are the ALM count, the DSP count, and the M20K count. If we're creating a design for the Agilex 5 Premium Dev Kit, which is the device pictured here, then we're going to have approximately 200,000 ALMs, 850-ish DSPs, and 1,600 M20Ks available to us. However, most of the time, there will be some additional application logic that you want to place onto the FPGA. This application logic might be part of a classic image processing pipeline, or it might be something completely unrelated. For the sake of today's demonstration, let's assume that half of the FPGA is used by some type of application logic, leaving the other half, only the other half, available for machine learning. One of the strengths of the AI suite is that you can adjust the size of the IP so that you only pay for the amount of machine learning logic that you use, and you don't pay for something you can't use. Since we're assuming half of the FPGA is used, that will give us about 100,000 ALMs, or give us a budget of about 100,000 ALMs, 420 DSPs, and 800 M20Ks. We'll specify that budget to the DLA compiler next. So let's do it. Let's run the DLA compiler again. This time I've included 3 new command line options shown in the tan colors here. The first of these is genarch. This tells the compiler that it should run the architecture optimizer tool on the input arch file. Remember, we said the arch file allows us to configure many parameters for the IP. This optimizer is an advanced tool to search that parameter space to find the best configuration for a given machine learning graph. We can ask the optimizer to either achieve a target performance and minimize area for that given performance, or we can ask the optimizer to maximize performance within a given area budget. In the case shown here, the second argument provides the compiler with my area budget. And so the compiler is going to run the arch optimizer and maximize performance within that specified area budget. The last option simply tells the compiler to put the new optimized arch file into an output file. Naturally, we called this my optimized arch. Let's take a look at the new performance and area estimate. The left-hand side shows the previous estimate of 335 frames per second. And the right-hand side shows the new estimate from the optimized arch file, which is 923 frames per second. Of course, there is a cost to this increased performance, which is shown in the area estimate. In the area estimate shown here, we've disabled the unused modules that were previously listed in the model analyzer report. Disabling these modules does not affect the performance of the graph, but it does reduce the area consumption of the IP. Comparing the old area estimate and the new, we can see that the area has increased by roughly 2x to 3.5x, depending on which resource we're interested in. When we look at this estimate in more detail, we can see that the M20K utilization came reasonably close to the area budget of 806 versus the 790 that we're actually using. Most of these M20K blocks are used in either the filter weight cache or the feature data cache, and both of these caches can be easily sized by the optimizer to achieve almost any target area. The 250 DSPs shown in the area estimate is somewhat below the DSP utilization allowed in our area budget, and this is simply due to the more heavily quantized nature of the convolution array. Typically, at some point after or before optimizing the IP, most FPGA designers will want to run inference on an actual FPGA board. Additionally, the data science team may want to do this in the case where they're doing co-optimization between the machine learning graph and the FPGA. We provide example designs for several families, including Agilex 7. The PCIe attached example designs are very easy to use and are great for deployment to the data science team to allow them to do exploration. We also have an SoC example design that can be used for further development by the embedded team. We're working on developing a hostless example design that has no attached host, and all of these example designs are in the process of being ported to Agilex 5. To summarize, we started with a YOLO V8 classification graph that we compiled for one of the example architecture files that was included in the AI suite itself. We then leveraged the model analyzer report to understand the performance of the graph. The model analyzer report showed us that some of the layers, the switch layers, were being mapped onto an attached CPU host. We learned that this will execute just fine using the example runtime, and that the unsupported layers will be transferred to that host either through PCIe or through the SoC connections with the example runtimes that we have. However, in our case, we then modified the arch file so that the graph would map entirely onto the FPGA. We then reran the performance analysis and saw the increased performance. And after that, we selected an area budget and ran the architecture optimizer to achieve a performance and area target specific to our assumed use case. We were able to do all of this just with the tools in the AI suite without access to hardware and without running Quartus. My hope is that you are now able to download the AI suite and then optimize and evaluate your own model. The Getting Started guide provides a walkthrough of the package, and the package itself can be downloaded either from Docker Hub or as a Linux package for your Linux-based system. One of our existing partners was able to come here today to tell us about their experience with the AI suite. Manu from Tiamu Networks, thanks for coming and joining us.
Very happy to be here, Tim.
Can you tell us about the product you're building?
Yeah, of course. Integrated sensing and comms is a bread and butter feature for 6G. Tiamu Networks is building this feature for NR and LTE today. At our demo booth, we are showcasing personnel sensing and localization purely using the NR reference signals that exist around us, all on the Altera family of devices, and of course, the FPGA suite.
That sounds amazingly complex. Can you tell us about some of the example architecture files that were included and how you evaluated the different arch files to choose one for your product?
Yeah, absolutely. We evaluate on many criterions, more simply based on the floating point availability, the layer supported, the efficiency that we receive in terms of throughput, clock speed, etc., and more critical infrastructure decisions such as the memory blocks, the DSPs, the LUTs, and the number of DMA transfers and the latency induced as a result of the heterogeneous deployments.
Wow, that's a lot of information to evaluate to choose the optimal one. It sounds like you must have used the estimator tools with the AI suite. Can you tell us about your experience with those estimator tools?
Yeah, and the estimator tools work wonderfully for us. The biggest challenge is that most of our architectures are non-standard, as well as our input data is completely non-standard in the sense that it will dynamically change, as does the scattering environment. As a result, we need to be very clear about the estimates that we will produce on our FPGAs and the fabric that we need. The estimator tool gives us not just a decent starting point to start off for any different architecture, despite these dynamic inputs and the dynamic architectures, as well as giving us, with some neat fine-tuning, the confident guesses that the impact of a specific deployment may have to us.
Wow, that sounds great. I really look forward to seeing your demo in the Customer Experience Center later today and to talking with you again.
Absolutely. Please come join us on our booth.
Thank you.
Altera, accelerating innovators.